All right, this is for 3.2a, differentiable functions. All right, so it says a function is differentiable on a closed interval from a to b if it has a derivative at every point within the interval. That means for whatever your picture looks like from a to b, there's going to be a tangent line with a slope that exists for every single x value from a to b. There's going to be a slope that you can have, a defined slope. And it says to verify this at any point, we must show that the left side and right side derivatives exist and are equal. So if let's say you're picking a certain value and you're not sure if there's a derivative there or if there's a slope that exists there, then you find the slopes directly to the left and the slopes directly to the right, and you keep getting closer and closer and closer. And if both of those derivatives are approaching the same value on the left side and the right side, no matter how close you get to that input you're picking, then you can say that the derivative exists. Now again, derivatives are slope values, and the only slope value that is undefined is when you have a vertical line. So if ever you have a vertical tangent, then your derivative cannot exist. All right, so it says sometimes derivatives fail to exist at a single point. So you have everywhere that you have a slope, but sometimes you're going to see a picture where there's going to be one point where there isn't a derivative. So what we're going to do is we're going to draw this picture right here. All right. So according to our piecewise function, we want to draw the line y equals negative x for all the values of x that are less than or equal to 0. So that has a point at 0, 0, and a slope of negative 1. So I'm just going to draw like that. And then to the right of 0, your equation is y equals 2x. So that goes through 0, 0 and has a slope of 2. Oops. There. Okay, sorry for the smudge. All right, so I want to know, does f prime of 0 exist? That's asking, is there a slope of a tangent line that exists at x equals 0? Well, remember that the derivative represents, there's my red pen. The derivative represents the slope of your curve at particular x values. Well, from x equals 0 to the left, the slope of this segment or this ray right here is negative 1. And the slope to the right here, all of these, because it's a line, it's linear, the slope is 2. Okay, now what I just read to you, it said that to verify at any point, we must show that the left and right side derivatives exist and are equal. So that means at 0, in order for there to be a derivative that exists there, the derivative on the left has to equal the derivative on the right as I'm getting closer and closer to x equal to 0. Now the thing is if you notice, this one, it's linear, so this slope here is going to be negative 1 no matter how close I get to x equals 0. And the slope on the right-hand side is always equal to 2. So in general, a function will not have a derivative at a point. In this case, we're saying it's x equal to 0 or 0, 0, where the derivative to the left of a, in this case is a 0, and the derivative to the right of a do not approach the same slope as you get closer to a. So as I'm getting closer to a from the left, the derivative is negative 1. As I'm getting closer to a or 0 from the right, the slope is 2, and it'll never become the same value. So therefore, f prime of 0 does not exist. All right, there are some functions that you need to become familiar with so that you know when sometimes a function is not differentiable at certain x values. Not differentiable just means that the derivative does not exist at certain places on your graph. One of them is y equals the absolute value of x. If I were to graph this function, it looks like this. It's a V shape. All right, this is called a corner. So that's what the previous example was. This is a corner. So at corners, derivatives do not exist because you can even see that the derivative on the left side will never equal the derivative to the immediate right side of that corner. All right, the other is called vertical tangents. Now, if you were to type in y equals the cube root of x into your calculator here and graph, here's what's happening right here in the middle. It actually looks like this, okay? And as you get towards the middle where like this change in concavity happens, there's a vertical line there. And there, your slope is undefined. And since the slope of the tangent line would be undefined there, it's therefore not differentiable, or no derivative exists because you can't have slopes of vertical lines. All right, the next one is a cusp. So let's see what this looks like on here. So in this case, I've got x squared, and I'm going to raise it to the 1/3. All right. So these ones look like the little birdies that you might have drawn when you were in kindergarten in the sky, and they tend to look like this. These are cusps. Right? So cusps are curvy. Again, you're going to have a derivative on the left side that never has the same value of derivative on the right-hand side. So those are called cusps. And then discontinuities, that's when you have any holes or jumps. Holes, jumps, vertical asymptotes, vertical asymptotes. Sorry about that. So it's functions like this. All right, so this particular function would not be differentiable at x equals 0 because there's a vertical asymptote there at x equals 0. All right, this next section of the notes, we have a picture here for us and then a few questions. So we are told that this function is defined on the closed interval from 1 to 5. And question 1 is, where is the function differentiable? So what's easier is just to see where is it not differentiable. So really what we're looking for is one of these or more of these 4 descriptions up here. So here, right, this little piece, notice it's curvy on both sides, so that's more of a cusp there. And then at 4, there's a hole, so that's going to be the discontinuities. So in this picture here, I would say for number 1, that so the function is differentiable on the interval from 1 to 5, except for x equal to 2 and 4. And just to be even more specific, I will say at 2, it is a cusp, and at 4, it's a discontinuity. All right, now the second one says, where is it continuous but not differentiable? That means where do you have a point that exists but you don't have a derivative there? So where do I not have a derivative? I don't have a derivative at 2 places. Here at x equals 2 and here at x equals 4. Well, continuous just means you have a point that exists for that input. So, and it doesn't jump around. It's part of the curve. So right here, you notice that I could trace this curve and not have to lift my pen even when x equals 2. So for number 2, this would be at x equals 2, that the graph is continuous, however, it is not differentiable there at 2. And then for 3, it asks, where is the graph not continuous and not differentiable? So both are not true, and that would be here at 4. It's not differentiable, and it's discontinuous because of the hole there. So that'd be at x equals 4. All right, the last part, it's a calculator exploration extra, and we're going to determine if this function y equals the square root of x squared plus 0.0001 plus 0.99 is differentiable at 0. So if I look at the graph, it looks like there's a corner there, so therefore it looks like there's no there's not going to be a derivative that exists at x equals 0. But what I want you to do is zoom in. So we're going to push zoom in, and I'm just going to push enter and see what happens as I keep pushing zoom in. If it lets me. Let's put it up. Zoom in again. Let's get up, zoom in again. Let's just see what's happening there. Zoom in again. So keep zooming in, enter again. And you can see in this case, you know, we have to just be careful that we don't assume based on what the picture looks like. If we zoom in closer and closer, you'll see that they're actually, the left side derivative and the right side derivative are actually approaching 0. So there is a derivative there. It's actually equal to 0. So just be careful. Sometimes you may have to zoom in a bunch of times to make sure, especially if you look at the function and you realize, oh, it's not one of those cubed roots. So maybe, and it's not an absolute value function, so possibly there is a derivative there.